The one thing which we knew that it would allow would be multiple colors of light, each carrying an individual signal, to be simultaneously amplified. Now that was profound. Because remember, up to that stage, one had tended to use just one color. And so you perhaps would get 10 gigabits per second on one color. But as soon as you had an amplifier which was agnostic to colors, it didn't care what the colors were, it didn't mix them up, they would just whiz through this amplifier, unchanged except much bigger. And that meant, for example, you could put 1,000 colors through, 1,000 channels. And 1,000 channels meant overnight we had increased the capacity of the world telecommunications installed base by a factor of 1,000 at least. We were provided with the telecommunications engineer's dream, the ability to string optical fibers across the world as a global cobweb with this vast capacity. And of course, without that, we wouldn't have the internet that we have today.
He's a remarkable person, as we all know, and the difference he's made to the field that he's concerned with, which is fiber optics, is just phenomenal.
What we figured out was when we made this rod, we could add down the core, during the fabrication process, this rare earth sequence. And then nature was kind to us, because it turns out that one of those sequence of rare earths, a dozen or so, has exactly the characteristics that we needed to make an amplifier to work at the wavelengths that optical telecommunications used. And that element is called erbium.
Well, he started off in the right place, Southampton, where there was a marvelous laboratory founded by a chap called Alec Gambling, and I think he must have been one of the first students there.
Glass tubing from which the fine fibre will be drawn.
So he was in fertile ground, but my goodness, he made the most of it.
The ability to transmit light is inserted.
And in particular, he was fascinated by the science, but equally fascinated by the applications.
The ORC has helped us to build the university's reputation overall, internationally, because of its huge profile in the big sphere of photonics.
Yes, I mean, there are a number of optics-based companies around this area that tend to cluster around the university. It's not, we've benefited from some of our very brightest people that have actually joined us from the ORC, whether they're at the graduate level or the postgraduate level, and they're a key part of our team.
And so they've been a vehicle for enhancing the reputation of the whole university, well outside of their own discipline.
David is fortunate in that he's been able to sustain his growing research group financially for many years. It's not really fortunate. It's primarily skill and primarily success. But he has been in a regime where it's been possible to do this.
The persons that develop our science policies tend to think in 5-year cycles, and sadly a technology cycle can be 50 years. And it's very difficult. You can't just dip in, put some funding into an area, and then when it doesn't produce something inside a few years, say, oh, well, that's enough, let's go somewhere else. It's leadership and understanding that that's what you've got to pursue, that that's the area which is going to be successful, and sustain the funding.
Selecting a Marconi Fellow is quite difficult, as all of us who've served on the selection committee know, because we look, of course, for somebody with great ingenuity and great intelligence and great success in science. But at the same time, we're also looking for somebody who's made a tangible difference to the community and to society at large.
We need to be able to tell the scientific story rather better than most scientists do. As scientists, nobody owes us a living. We need to be successful, we need to create wealth, well-being within the peoples of the earth. And to do that, we need to explain to people why we are the ones that have the solutions to the future.